In section 7.6, we look at the binomial theorem. Let's start by considering powers of the binomial a plus b. So we know that if we take a plus b and raise it to the first power, we get a plus b. A plus b to the second power, if you FOIL this, you end up getting a squared plus 2ab plus b squared. A plus b to the third power is this, and I'll just quickly show the work for that. So a plus b to the third power is a plus b times a plus b times a plus b. And then we know that a plus b times a plus b right here, that's a plus b squared. So I can just replace it with this. And then if I multiply this out by distributing here and distributing here, we end up getting a to the third power plus 2a squared b plus ab squared plus, down here we have b times a squared, which is a squared b, plus b times 2ab is 2ab squared, plus b times b squared is b to the third. And when you combine like terms, you get a to the third plus 3a squared b plus 3ab squared plus b cubed. And so remember here we have coefficients of 1, right? So we're just adding like terms there. So this is what we end up with, and that is right here. Now, you can keep doing this. So to get a plus b to the fourth power, you can actually just take this result and multiply it by a plus b. But it's kind of a lot of work, and you would end up getting this. And you can see that each time you multiply by an additional factor of a plus b, it gets more and more complicated. And so in this section, what we want to do is explore whether or not there is an easier way to get these products. And there is, and it's called the binomial theorem. One of the things that I want to do is point out some patterns that occur when you multiply powers of a plus b. So just look at the result for a plus b to the fifth power. What I want you to notice about the variable a is that in each successive term, the power of a is decreasing by 1, right? So we have the fifth power, and then the fourth power, third power, second power, first power, and then here there's no a at all, which means a to the 0. Likewise, the power of b is increasing by 1 every single time. So here there is no b, which means we have b to the 0, and then here we have b to the 1, and then b to the 2, b to the 3, b to the 4, and b to the 5. The other thing I want to point out is that if you look at any one of these terms in particular, the sum of the exponents is always 5. So here the exponent is 5. Here, if you add those exponents, 4 plus 1, that's 5. If you add these exponents, you get 5, right? And we can keep doing this. For every single one of these, if you add the exponents together, you get 5. And that is because the original power here was a fifth power. So the power of a decreases every time, the power of b increases every time, and the power of a plus the power of b always has to equal the power that you started with here. So the only thing that comes into question next is how do we get these numbers in front of the variables? And these are called the binomial coefficients. How do we get these numbers? Well, we're going to spend a little bit of time talking about that. But first, let's just make sure we understand this concept. In our first example, we want to consider the expansion of a plus b to the fourth power. They want us to write down the variable parts of all the terms that occur in the expansion. So remember, the power of a decreases, the power of b increases, and the power of a and b should always add up to be 4 in this case. So the first term of the expansion is going to have an a to the fourth. The next term is going to be a cubed times b to the 1, right? So the power of a decreased. And now we're bringing in the power of b, and notice that 3 plus 1 is 4. In the next term, we're going to have a squared times b squared, and then a to the 1 times b cubed, and finally, b to the fourth. Now, I'm not expanding this, I haven't multiplied it because I don't know what the coefficients are going to be for this. We're going to talk about that in a minute. But for part B, it says, what is the sum of the exponents for a and b? And again, we just mentioned that, but if you add the exponents for a and b in any one of these terms, the sum is always 4. All right, let's talk about those coefficients now. Before we can talk about the coefficients, we have to define something called a factorial. The definition for a factorial is let n be a positive integer, then n factorial is defined to be n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1, okay? And the quantity 0 factorial is defined to be 1. So let's go through a few examples just to make sure we understand this. So 0 factorial equals 1. And yes, the exclamation point is what we call the factorial in this. 1 factorial would just be 1. 2 factorial, the definition says you take the number 2 and you multiply by successively decreasing numbers until you get down to 1. So 2 factorial would just be 2 times 1, which is 2. 3 factorial would be 3 times 2 times 1, which is 6. 4 factorial would be 4 times 3 times 2 times 1, which is 24. And we'll do a couple more here. 5 factorial would be 5 times 4 times 3 times 2 times 1. This turns out to be 120. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, which is 720. And finally, 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And this number turns out to be 5,040. So a couple of things. Getting factorials is a pretty easy process once you get used to the idea. And the other thing is they get pretty big pretty fast. So for example, if I wanted 8 factorial, right? We know that 8 factorial is going to be 8 times 7, 6, 5, 4, 3, 2, 1. What I could do is I could just say that 8 factorial is 8 times 7 factorial. And that would be 8 times 5,040. And this would be 40,320. So again, they get really big really fast. And it turns out that these factorials are actually really, really useful in lots of things in mathematics. And one of them is finding the binomial coefficients. So the definition of the binomial coefficient is we're going to let n and r be non-negative integers, and r has to be less than or equal to n. In the expansion of a plus b to the nth power, the coefficient of the a to the n minus r times b to the r term is this thing right here. And this is what we call a combination. You don't need to know that, but this is called a combination. And the way we pronounce this is we say n choose r. Okay, that's how we say that. And n choose r is defined to be n factorial divided by n minus r factorial times r factorial. And I know that can be a little bit tricky, but let's go ahead and take a look at some examples down below here. Now, the first example here is a simple factorial. They ask you to calculate 5 factorial. We did this on the previous page, but let's go ahead and do it again. 5 factorial is simply 5 times 4 times 3 times 2 times 1, and this is 120. Now for part B, this is a combination. We're looking at 6 choose 3. And the definition of n choose r is you take the top number and you put it on top with a factorial. So for this one, we're going to take this top number, which is 6, and we're going to put it on top and put 6 factorial there. And then in the bottom, you're going to take the top number minus the bottom number, factorial. So that's going to be 6 take away 3, factorial. And then don't forget, you also have to multiply by r factorial, and that's just the bottom number factorial, which in this case is 3 factorial. Now we just have to do the math. So this is 6 factorial divided by, right here, 6 minus 3 is 3, so that's 3 factorial times 3 factorial. And now we'll just expand it. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, divided by 3 factorial is 3 times 2 times 1, and then 3 factorial again is 3 times 2 times 1. And there's lots of ways you can simplify. Rather than multiplying everything out, what I like to do is cancel common factors. So 3 times 2 times 1 will cancel out with 3 times 2 times 1. And then 3 times 2 times 1 here, that's equal to 6. That will cancel out this 6 right here. And so all we have left over in the end is 5 times 4, which is 20. And so 6 choose 3 turns out to be the number 20. Let's do one more to make sure we understand the concept. So for the last one here, we're looking at 5 choose 2, right? That's this one right here. And the way we do that is we take the top number, which is 5, we put a factorial on it. Then we're going to subtract the top and the bottom number, so 5 take away 2 factorial. And then we're going to take that bottom number, which is 2, and put a factorial. And so this is 5 factorial divided by 3 factorial times 2 factorial. And when you expand it, it's 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 2 times 1. And again, I'm just going to cancel what I can. So 3 times 2 times 1 cancels with 3 times 2 times 1. And then 2 times 1 is 2. And that 2 right there will cancel the 2 and the 4 and leave you with a 2 left over there. So in the end, we have 5 times 2, which is 10. And so the combination 5 choose 2 is 10. Well, it turns out that these kinds of computations are exactly how you figure out those binomial coefficients in the binomial theorem. Let's talk about the binomial theorem. So I know this is going to appear to be kind of complicated, but it's not too bad once you get used to it. So the binomial theorem says if you have the binomial a plus b and you want to raise it to the n power, where n is some positive integer, then you can do this by taking the summation I equals 0 to n of n choose I, a to the n minus I times b to the I. And if you plug in I equals 0 in here, you end up getting n choose 0 times a to the n. If you plug in I equals 1, you get n choose 1, a to the n minus 1, and times b to the 1. And if you let I equal 2, you get this term, and so on all the way down to the end. So this is how we can expand a binomial raised to a power without having to do all the work of multiplying it out and foiling and all that kind of stuff. So let's just take a real quick example. Suppose I wanted to do a plus b to the third power, right? So n is equal to 3. So I'm going to put a 3 here, and I'm going to put a 3 here. So this would be the sum I equals 0 to 3. 3 choose I. A to the 3 minus I, right? So I'm putting a 3 everywhere I have an n. And then times b to the I. Okay? That would be the setup. Now, this is going to be, if I let I equal 0, I'm going to put a 0 in everywhere I see an I. That's going to give us 3 choose 0, a to the 3 minus 0 times b to the 0. Plus, the next term, I'm going to plug in I equals 1. That will give us 3 choose 1, a to the 3 minus 1, b to the 1. If I let I equal 2, I get 3 choose 2, a to the 3 minus 2, b to the 2. And if I let I equal 3, which is the last term, I get 3 choose 3, a to the 3 minus 3 times b to the 3. And now to get the answer here, all we have to do is two things. So we have to simplify all these exponents. That's really simple to do. And then we have to calculate all of these binomial coefficients. So let's do those down below here. And I don't think I'll show all the work on these. I'll just write it out and we'll magically make it appear on the screen. All right, so here is all of the work to figure out these binomial coefficients. And I know this might seem a little bit excessive, but trust me, once you get used to doing this, it's not that bad. Plus, I'm going to show you another way to figure these out that's a little bit simpler. But all I got to do now is take these numbers. So 1 corresponds to this one, right? So we're going to have 1, and then a to the 3 minus 0 is a to the 3rd. And then b to the 0 is 1. And then this one here, 3 choose 1, that's 3. So we're going to have plus 3a squared b to the 1, right? That's these here. Plus the next one, 3 choose 2, that's this number right here, which is 3a to the 1, b to the 2. And finally, we have 3 choose 3, which is this number right here. And that gives us a to the 0 times b to the 3rd. Okay? So if you take a look at that, we can go back to the first page to show you that it's the same thing. So here it was on that first page, a plus b to the 3rd power was this one, right? And we actually multiplied it out, if you remember. So we get the same thing. Right? Same thing right here. Okay, so now let me show you another way to get these binomial coefficients. It's called Pascal's triangle. Pascal's triangle is a triangle of numbers. So you'll make this triangular pattern. And the question is, how do you get these numbers? Well, at the top, we start with 1. And then for the next row, we put 1 and 1. And now here's where it gets interesting. To get the next row, all we do is we add these two numbers together right here to get 2. So 1 plus 1 is 2. And on the end, we always have a 1, right? So you'll notice that we always have a 1 on the end here, right? To get the next row, 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Right? 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And etc. Right? So this goes on forever and ever and ever. Well, if you look at this particular row right here, the 1, 3, 3, 1 row, this should remind you of what we did on the previous page, right? The 1, 3, 3, 1, those were the coefficients of the binomial expansion a plus b to the 3rd power. So you can use Pascal's triangle to help you get the coefficients and not have to go through all of this computation that we did down here. Now, you can do it either way. I'm not suggesting one way is better than the other, but many students prefer Pascal's triangle. All right, so let's use Pascal's triangle to do another example here. let's do the binomial expansion of a plus b to the sixth power. Now, the first thing you need to ask is which row corresponds to the sixth power. So just to give you a real quick reference here, the top row corresponds to a plus b to the 0, and we never have to use Pascal's triangle for this. The second row corresponds to a plus b to the first power. The third row corresponds to a plus b to the second power, right? So what that means, for example, when you multiply out a plus b to the second power, you get a squared plus 2ab plus b squared, right? So what you have there is the 1, 2, 1 that you see here, okay? A plus b to the third power corresponds to the fourth row. So if I want to find the expansion for a plus b to the sixth power, I need to find the row that corresponds to a plus b to the sixth power. And that's this row right here. Now, there is kind of a quick and easy way to do this, and this is sort of the shortcut that I like to use. If you have a particular power that you're looking for, all you got to do is look at the second number in the row, and that number has to match the power that you're finding, right? So notice that the second number always matches the power. Second number always matches the power, right? For every single one of these. So if I'm looking for a plus b to the sixth power, I'm going to use these numbers in the expansion. So now let's go ahead and do that expansion. So this is actually quite pleasant. What we're going to start off with is 1, and then you know it's a to the sixth power, plus. Then we're going to have 6, a to the fifth power, b to the first power. And then 15, a to the fourth power, b to the second power. So remember, the power of a goes down by 1 each time, and the power of b goes up by 1 each time. So next we have 20, a cubed, b cubed, and then 15, a squared, b to the fourth, and then 6, a, b to the fifth, and finally 1, b to the sixth. And there it is. And you have to admit that that is much easier than multiplying a plus b times itself 6 times, right? So once you have Pascal's triangle, getting these binomial coefficients is actually pretty simple. So for our next example, we want to expand a binomial raised to the fourth power, but this time you'll notice that instead of having a plus b on the inside, we have 3 plus 2y. So 3 is like our a, and 2y is like our b. So if I use the formula to do this, 3 plus 2y, quantity to the fourth power, is going to be the sum I equals 0 to 4. Then we're going to have 4 choose I, and then a is 3, so it's going to be 3 to the 4 minus I. And then b right here, that's 2y, so that's going to be 2y to the I power. So that would be the setup. So you have to substitute a equals 3 and b equals 2y into here and here, in addition to letting n, in this case, be equal to 4. Now you can go ahead and expand this out by plugging in I equals 0, 1, 2, 3, 4. But actually, I'm just going to use Pascal's triangle to get these coefficients right here. So here is Pascal's triangle, and since we are doing a fourth power, right, we're going to choose this row. So here we go. What we're going to have is 1 multiplied by 3 to the fourth power, plus. Then we're going to have 4 multiplied by 3 to the third power, and then 2y to the first power. So again, the power of 3 decreases every time, and the power of 2y increases every time. So the next one's going to be 6 times 3 to the second power times 2y to the second power, and then 4 times 3 to the first power times 2y to the third power, and finally 1 times 3 to the 0 power times 2y to the fourth power. And now we just have to do the arithmetic. So 3 to the fourth power is 81, plus, then here we have 4 times 3 cubed, which is 27, times 2y to the first power is 2y, plus 6 times 3 squared is 9, times, now right here we have to square the 2 and square the y. So 2 squared is 4, and then times y. Then we have 4 times 3 times, here we have to cube the 2. 2 cubed is 8, and then y cubed. And then we end up with 1 times 1, and then 2 to the fourth power is 16. So we have 16 y to the fourth. And then we have to just do the multiplication. So we have 81 plus 216 times y plus 216 times, oops, this is supposed to be y squared right here. I made a mistake there. There we go. Plus 96y cubed plus 16y to the fourth. And you could leave your answer like this. That's fine. Sometimes what they'll do is they'll flip it around. So they'll put this term first, this term next, right? They'll write it in descending order, but this is okay for what we're doing here. But notice that I didn't have to use the definition of 4 choose I to get all these coefficients here, right? I just got these numbers here from this row of Pascal's triangle. Now, another thing I want to point out is you don't end up with those numbers in the end, right? You'll notice that the numbers are different. Well, that's because we had numbers inside of here, and those numbers were also affecting the result. Let's do one more. So here we want to expand 2z minus y to the fifth power. So the first thing you need to do is you need to write this as 2z plus negative y to the fifth power, because your binomial theorem is for a plus b. So if you have a minus sign, you have to put plus a negative, which is what I did here. Now, using the binomial theorem, this is going to be the sum I equals 0 to 5. 5 choose I, and then we will have 2z to the 5 minus I multiplied by negative y to the I. And again, one way to do this is just start plugging in I equals 0, I equals 1, etc. But I'm just going to go to Pascal's triangle because it makes the process so much easier. So here is Pascal's triangle, and since we are doing a fifth power, we will look at this row right here. Hope you guys can see that okay. Those numbers are 1, 5, 10, 10, 5, 1. Okay, so those are going to be the numbers that we get here when we plug in I equals 0, 1, 2, 3, 4, 5. And so down below, we can go ahead and start expanding. We are going to start with 1, and then we will have 2z to the fifth power, plus, next term we will have 5 times 2z to the fourth power, and then we have to bring in our other factor, which is negative y to the first power. Next one's going to be 10 times 2z to the third times negative y squared. And then 10 again times 2z squared times negative y to the third. Plus, next one's going to be 5 times 2z times negative y to the fourth. And finally, we have 1 times negative y to the fifth. So again, the power of negative y goes up by 1 each time, and the power of 2z goes down by 1 each time. So now we just need to do the math on this and take it slow here. It's easy to make mistakes. So right here we have 2 to the fifth power times z to the fifth power, plus we have 5 times 2 to the 4th power times z to the 4th power times negative y, plus 10 times 2 to the 3rd power times z to the 3rd power, times, now negative y squared is just y squared, right, because the negative cancels. Plus, then we have 10 times 2 squared, that's going to be 4z squared. And then we have negative y quantity cubed, that's going to be negative y cubed. Plus, then we have 5 times 2 times z. Negative y to the 4th is y to the 4th. And finally, we have minus y to the 5th. So again, when you raise a negative to an odd power, the negative stays. When you raise a negative to an even power, the negative goes away. So let's just simplify this now. 2 to the 5th power is 32, so we have 32z to the 5th. Now our next term is 5 times 2 to the 4th is 16. 5 times 16 is 80, but then there's a negative 1 right there, so that's going to be negative 80 z to the 4th power, y to the 1st power. Our next term, we have 10 times 2 cubed. 2 cubed is 8, so 10 times 8 is 80 once again. We have z to the 3rd power, y to the 2nd power. Next term, we have 10 times 4 is 40 times negative 1, so that's going to be negative 40. Z to the 2nd power, y to the 3rd power. Next term, we have positive. 5 times 2 is 10, so that's going to be 10z times y to the 4th. And our last term is minus y to the 5th. And so there is the expansion of 2z minus y quantity to the 5th power. And again, I know this seems like a lot, but once you get used to this process, trust me, it's way better than multiplying everything out. Let's talk about one last thing. Suppose you have a binomial expansion and all you want to do is find a particular term in that expansion. So let's say you want to find the ith term in a binomial expansion. So if n and I are positive integers, the ith term of a plus b to the n power is given by this formula. So it's n choose I minus 1, and then it's a to the n minus I plus 1 times I minus 1. All right, so I know this is kind of a lot to keep track of here, but let's do an example. Suppose we want to find the 4th term of 3x plus 5 to the 6th power. So the formula says you are supposed to take n choose I minus 1 times a to the n minus I plus 1, and then b to the I minus 1. So the key is this. If I'm looking for the 4th term, the number in the bottom here is always going to be 1 less than the number that you're looking for, right? So in this particular case, we can see that n is 6, so we're going to have a 6. And since we're looking for the 4th term, we're going to put a 3 there, right? Because 4 minus 1 is 3. That's what this tells us. And then you have a to a power and b to a power. Now a is 3x and b is 5. And the question is, what are the powers going to be? Well, what I want you to notice is that whatever this number is in the bottom here, it's the same as the power of b. So if I have a 3rd power down here, I'm going to have a 3rd power here. So the only other thing to figure out is what is the power of 3x? Well, the formula says it's n minus I plus 1. You don't need to do all that. You know that the power here, when you add it to this power, has to equal 6, right? Because the power of each of these has to add up to be 6. So if this is 3, this would also have to be 3. Now you can do this. So you can say that since we're looking for the 4th term, we take 6, we subtract I equals 4 and then plus 1, and this is equal to 3, right? So that's the other way you can figure this out. But to me, it's much easier just to know that these always have to add up to be this number right here. So now we just need to figure these things out. So 6 choose 3 is 6 factorial over 6 minus 3 factorial times 3 factorial. And then we have times 3 to the third times x to the third times 5 to the third. So this is 6 times 5 times 4 times 3 times 2 times 1 divided by right here. This is 3 factorial, so that's 3 times 2 times 1. And then we have another 3 factorial times 3 to the third is 27, so 27x cubed. And then 5 to the third is 125. So now I just need to do some cancellation. 3, 2, 1 cancels here. And 3 times 2 times 1 is 6. So we end up with 20 times 27 times 125 x to the third. So now I just need to multiply 20 times 27 times 125. And when you do that, you get 67,500 x to the third. So what do we do here? Well, if you took this whole thing here and you multiplied it out, the fourth term would be this term. Okay, so we just found one of the terms of that expansion.